Welcome to part 3 and 4 of the Chemistry of Water Lab. In these sections, we're going to talk about salinity in part 3 and pH in part 4. When you think of chemistry of the ocean, probably one of the first things that comes to mind would be salinity. And that's what we're going to focus on now. Now, in terms of salinity, the thing you probably recognize the most is salt, sodium chloride, NaCl. And salt's a really interesting compound, essentially because of its components. Sodium is actually rather volatile, and chlorine, you know, is rather poisonous, right? We put it in our swimming pools, but we have to be very careful with the concentrated amount. But you put it together in a bond, and you put it on French fries, which is just kind of mind-boggling, right? Let's look at the chemistry behind what happens with this bond just really briefly. So looking at the good old periodic table, sodium is over here in the third period or the third row, and it has one valence electron, which means it's not really very happy. It's wanting to react with things because it wants a full valence shell. Chlorine has 7 valence electrons, but it needs one more to have a full shell. So to break down the jargon and make it simple, essentially what happens, sodium donates an electron to chlorine. And when that happens, sodium becomes a positive ion and chlorine becomes a negative ion. And those positive and negative charges attract to create an ionic bond. And that is what we call sodium chloride, right? Salt. Now, water plays a big part of this because water is a polar molecule. It disassociates sodium and chloride into their ions, Na plus and Cl negative. But of course, water is a pretty awesome molecule to begin with. However, now let's check it out. How do we actually measure salts in water? Well, first, understand that salts in water, in seawater, it's not just sodium and chloride. There are other things like magnesium and potassium and calcium and things like that. So if you actually go to a store and buy a bucket or a box of salt to mix for an aquarium, you're going to notice that there's a lot more in there than just sodium chloride. However, by percent weight, sodium and chloride do make up the largest components. But that still being said, what scale do we use to measure this in? So salts in general are called inorganic constituents, and we measure them in what we call ppT, or parts per thousand. We can also represent that by a percent sign, like you're used to, but this is out of 100, add another 0, it's out of 1,000. So you'll often see both of these in the various literature. Now, there are other ways to measure salinity as well, but this is the most common for science classes and aquariums for us to look at. Now, there are a couple of ways to look at this and think of it conceptually. Let's say I had 1,000 of these beakers, and out of those 1,000, all of them were filled with water except for 35 of them, but 35 of them were filled with salt. Then I took all 1,000 and mixed them together, the 35 with salt and the rest with water. The mixture would essentially be 35 parts per 1,000 salinity. All right, that's essentially what we're looking at. Now, why am I using 35 parts per 1,000? 35 represents the general normal oceanic salinity that you find. All right, there's some variability here and there, up and down, 35 to 37, things like that. But that is essentially the average that we tend to find in open oceans. Now, freshwater would be more close to 0. And of course, there's a range in between. If you go to some areas that have maybe a lot of freshwater discharge, you might find areas that are 15 parts per 1,000, 20 parts per 1,000. If you go to areas like the Dead Sea or the Great Salt Lake, you're going to find hypersaline environments that are very brine or salty that might be closer to 50 or 60 parts per 1,000 or even higher. So there is a range of salinities that we can find depending on where you go. Now, most aquariums tend to keep it around oceanic salinity or sometimes a little lower, simply to prevent disease, things like that. So now let's look at how we actually measure it. What are the tools? One of the tools we have is a hydrometer. This one is actually from the aquarium store. It's really easy. You fill it full of water and the little floating tab will tell you essentially what the reading is, and it has it in parts per 1,000. It also has a specific gravity scale. We're not going to get into that technicality yet, but that's there. The other way, in which I'm going to focus on a little bit more, is a refractometer. And this is a really cool device where you essentially put a little bit of water here on the glass plate and look into the viewfinder to find out what the salinity is. There's a scale in there. So let's get a little bit more in depth in how to work the refractometer. Now, a refractometer works because it uses the idea that as there are a higher amount of inorganic constituents in the water, the light will actually bend differently as it passes through the light. And so when we put water on this glass plate, the light is going to go through it and it's going to get bent, and then it's going to get collected and piped through the rest of the instrument. So let's look at this in a diagrammatic form. So I am going to use the blue as the water. This is the faceplate. And if I put a little water on the faceplate, there we go. And I'm going to use red so you can see it as light. The light comes down from the sun. It gets bent, and this purple blob right there represents a prism. And that prism, again, helps bend the light towards some of these optical components and lenses. And so the light gets bent and shown through to the scale. And from that scale, where there is an actual calibration knob, and we're going to talk about that in a minute, you eventually are able to see what's going on through the eyepiece and where the salinity falls along the scale. Now, we of course do have a calibration knob, and this is really important for all instruments because we want to make sure we are reading correct and accurate information. And so what is the actual accuracy of a refractometer? Well, let's look at some of the components from the manufacturers. First of all, the range is from 0 to 100 parts per thousand. So that's essentially where we can read measurements. If it's above 100 parts per thousand, it would not be able to. Now, under almost all circumstances that we deal with, you're never going to need something that's over 100 parts per thousand, especially in the aquarium industry, or even a lot of what we do in the ocean. And you're obviously 0 is as low as you can go. Accuracy is really important. It's plus or minus 1 parts per thousand. So if we are getting a reading that is 35 parts per thousand, we would say then it's 35 parts per thousand plus or minus 1 part per thousand. So that means it could be 36, it could be 34. But 35 is where we're going to put it. So it's always important to know the accuracy that you have within any instrumentation. Now that we're familiar with salinity, let's get out in the field and collect some samples. So we're here at Lake Osborne, and this is going to be our first water sample of the day. All right, we are here at site number 2, and this is the Lake Worth Lagoon. So let's get a water sample here too. All right, we're here at the beach for our third sample, and oftentimes this time of year, there's actually a tropical depression out here causing a little wave action too. Let's get some samples. All right, now we are ready to deal with the samples we collected. So we are actually going to be processing 4 samples. The first 3 will be from the field, which you saw the video on, and the 4th one is actually from my 75-gallon tank here at school. But before we do that, we need to calibrate the instrument. And so right here, I have some distilled water that I got at Publix. It's deionized. I'm going to pour this in a beaker, just a little bit. And I'm going to go ahead and add just a little bit of this to the faceplate to make sure that it's reading 0, because that is important. If I compare this sample to the others, I want to make sure it's accurate, especially to that 1 part per thousand plus or minus accuracy. So let's look at this and we'll see where we are and it's just off of 0. So I have the little calibration knob there. It's great for a little fingernail or a small screwdriver, and I'm on 0. So it is now calibrated, ready to go. So I can just rinse off my faceplate and we can begin with our samples. So let us go ahead and start with the lake sample. Where is it? The lake sample is in the lovely Tostitos container. There we go. And let's see what we got. Looks a little green in here, I'll tell you that. However, I'm expecting this to be close to 0, if not 0 as is. And we are correct. It is 0. So sample number 1 is 0 ppt. So now this is my wastewater. I'm going to use the distilled water, kind of clear out my pipette. And now let's move to sample number 2, which is going to be the lagoon. All right, this one looks like it's going to be 25 parts per thousand, and it's in the lagoon. Now, if you noticed in the video, what was it doing? It was actually kind of cloudy and it had just rained. That might have actually brought the salinity a little bit down too. Also, there's canal discharge, things like that. So it makes sense that it would be a little bit less than oceanic water. So let's move on to the third, which is ocean water. Let's see what we got with the ocean water here. All right, let's see what we got here. And this one is almost right on the line of 35 parts per thousand. T's are starting to look like X's. And the last sample we're gonna do is from the tanks. So let's check this out and see what we got. Probably about 30, 31, 32. I'm gonna call it 32 parts per thousand. All right, so now make sure to document this on your lab form and figure out what category you think that the readings are. Are they freshwater? Are they brackish? Are they ocean salinity? Are they brine, hypersaline? What do you think? Let's go ahead and get started with part 4 of the Chemistry of Water lab. And that's all about pH. Now, pH is an incredibly important parameter within the marine environment and freshwater habitats as well. Now, when we talk about pH, we're talking about a scale from 0 to 14, with 7 being neutral, below 7 being acidic, and above 7 being basic. Now, what are we really talking about when we talk about pH? We are talking about the concentration of hydrogen ions. In fact, pH means the negative equals the negative log of hydrogen ion concentration. Now, where does hydrogen ions come from? Essentially, water dissociates into hydrogen ions and hydroxide ions. The hydrogen ions can sometimes bond with, of course, other water molecules, making hydronium, which is H3O+. Now, hydrogen ion concentration is sort of all contained in there, right? Both hydrogen and hydronium. Now, the higher the hydrogen ion concentration is, the more acidic your solution is. The lower the hydrogen ion concentration, the more basic you're going to be. Now, when we look at the ocean, the pH tends to be around 8, 8.5, right? There's some fluctuation there. In rainwater and some freshwater, you can get down to about 6, so slightly acidic. Now, in some freshwater, especially here in South Florida, because we have a lot of limestone in our ground, we can actually get readings of 8 and 9 as well in freshwater. So there is a range here which is suitable for living organisms in aquatic environments, depending on where you are, what type of environment you're in. But of course, in the ocean, we do have some issues with what we call ocean acidification, where we start to decrease the pH and increase the acidity. And this can cause problems with coral growth. It can cause problems with various different types of arthropods, crustaceans, anything that has a calcium carbonate skeletal system, exoskeleton or endo, it can have a big problem with that. So of course, measuring pH in the field is really important. And we are going to be measuring pH using a digital meter. Now this digital meter is really quite useful, but just like any other utensil and tool that we take out into the field or in the lab, we need to make sure that it's accurate. Now, this particular pen, they call them pens sometimes, has an accuracy of 0.1 pH. So that is how accurate it can measure pH down to. How do I know that? I look at the directions provided in the packaging and the manufacturing that we go. Now, we're also going to look at calibrating this to make sure that we are as close to that accuracy capability as possible. And to do that, most of these digital pens and meters have calibration modes. And that's what we're going to get into now. So what I have here are 3 different liquids. One is a pH of 7, one is a pH of 4, and one is a pH of 10. And so once I put the pH meter into calibration mode, I'm going to dip it in each of the different solutions and it's going to calibrate to those different pHs. Once it's through calibration mode, we should be able to have accuracy that reaches that 0.1 accuracy for pH readings. All right, it's time to go into calibration mode. And we're going to enter into pH 7 first and let it go. And we are done. We have the calibration finished. I'm just gonna do a last rinse off of the probe. All right, our pH meter is calibrated and ready to go. And now I have the samples from the field that we had collected, same samples we did the salinity with, and we're gonna check out those values. However, we're gonna start with distilled water. Now this is just a jug of distilled water I got from the grocery store. And we're gonna try that first because it should be about 7. So let's check this out and see how we go. Now we do have to let it sit here just for a minute to kind of stabilize. And there we are. It looks like we have a reading of about 7 on the pH scale. All right, so now let's check out our lake situation here in the Tostitos container. Now I just rinsed off in distilled water, so my probe is now clean. So let's try this. And again, we'll let it stabilize. And it looks like we're at 7.7. All right, I'm gonna clean off my probe and catch up on a little data here. So the distilled water was a 7. Our lake was 7.7. Now, let's get to our lagoon. Okay, it looks like the lagoon is 7.62. I'm going to do a little rinse off here and write my numbers down. 7.62. Now let's go for the ocean. Let's see what we've got going on here. And our ocean is looking like it is 8.07. Clean that out. 8. Wow. I can't write sideways. 8.07. So if we look at these values, do they make sense to what we know? Distilled water should be about neutral. That makes sense. Now the lake water is a little higher than 6, so it is just over 7. Why would that be? Well, there is a little bit of buffering because of all the limestone in the lakes, things like that. But it's still reasonably low. And the lagoon, which is a brackish body of water, is 7.62. Now, these two are within a particular margin of each other. It makes sense because there is fresh water that actually gets dumped out into the lagoon. Also, it had just been raining recently when we collected that sample. That way would tell us that that might bring the pH down a little bit as well. And the ocean is at 8.07, so that is where it should be within range. And again, because of the rain that had just happened before we got to the beach, it's very likely that the surface waters that I was getting the sampling in might have brought it down just a hair. And maybe it would have been maybe 8.3, 8.4, you know, if it wasn't for that. I don't know, but those are options. But these do make sense based on what we know of pH in the field. So we have really explored quite a few different aspects of the chemistry of water today. And I don't know about you, but water is actually pretty cool.
Without water, we wouldn't have such awesome things like Kool-Aid, thanks to water's ability to dissolve many types of solids.
Not to mention, I'm kind of fond of the ocean, and I'm kind of glad it has salt in it. So until next time, keep learning.